So the next topic is determination of the derivation of equilibrium equations for three-dimensional body or element. Okay. So see, this is an three-dimensional body which is subjected to the different types of forces. Okay. So we can say that the if it is a body is a one-dimensional body, the forces, the stresses which are developed in one-dimensional body is only the axial stress, that in only particular direction on which it is load is applied. So similarly, for two-dimensional body, we are having three stresses. So two axial stresses and one shear stress will correspond to the stress we used to have this strain. So next, coming to a three-dimensional body, we are having three types of stresses. So three stresses and for three-dimensional body, we are having totally 6 stresses, in which 3 are axial stresses and 3 are shear stresses. Okay. So now we are going to derive the equations for equilibrium equations for three-dimensional body. Okay. So equilibrium equation, when the body is said to be in equilibrium means when the sum of forces acting on the body is equal to 0, then only we can say that the body is in equilibrium. Okay. So now let us consider a small elemental volume of cube elemental cube of volume dV. Okay. So let the length of the element is assumed to be, this length of the element is assumed to be dy, and height of the element is assumed to be dz, and width of the element is said to be assumed to be dx. Okay. So now let us consider the force which is applied in x direction. The axial force applied in x direction. See, this is the one of the plane. This is one plane. So on one plane, I used to have one axial stress and two shear stresses. Because of it is a three-dimensional element, it corresponding to the load applied in the x direction. There will be deformation occurs in the y direction and z direction. The z direction and y direction also. So here the load is applied in x direction. The stress which is developed in x direction is nothing but sigma x. So after applying the load, the body will be deformed, and the deformation which is produced in the body is represented by symbol dou sigma x by dou x into dx. Okay. So here the change in the stress produced due to load applied is represented by dou sigma x by dou x into dx. Okay. So similarly, I am assuming that the body force is going to be applied on the body. On x direction, I am assuming the total body force applied is f of x into dv. Okay. So f of x into dv. Okay. So now we are going to derive the equilibrium equations on the body. Okay. So see, let us we are presuming the displacement vector u is equal to u, v and w transpose. So here the u, v, w are representations for displacement on particularly x direction, y direction and z directions respectively. So u symbol is represented to represent displacement in x direction, v is used to represent displacement in y direction, and w is used to represent displacement in z direction. Okay. So as I said, work potential is nothing but work done by the external force of the body with application of the external force. So here whatever the work done by applying the external force on the body is said to be as work potential. So if work potential is developed due to the application of body force, so what is body force? Body force is nothing but force which is distributed over the entire volume is considered as body force. So hence we can consider integral of f of u into f into u transpose dv. So the integral limits are from 0 since it is distributed over the entire volume, we can consider it as integral over the volume f into u into dv as work potential for body force. Similarly, traction force. What is traction force means? The force which is distributed over the entire surface is considered as traction force. Hence I can consider it as integral over the s surface area T into u into ds is represented as work potential due to the traction force. So similarly, point load. So work point load is since point load is concentrated on only vertical point, I can take the summation of I is equal to 1 to n pi ui, which is considered as work potentials due to the body force, traction force and point loads. Okay, so as I said, the body should be in equilibrium. As a body should be in equilibrium, the sum of forces which is acting on the body should be equal to 0. Hence, I am assuming that the total forces in x direction f of x is equal to 0, total force in y direction f of y is equal to 0, and total force in z direction f of z equal to 0. Okay, so just we are revising the Hooke's law equation. So the Hooke's law states that, so we know that from Hooke's law, stress is directly proportional to the strain. Okay, so Hooke's law, stress is directly proportional to the strain. Okay, so as I said, for one dimensional body, we are having only one stress, and so as I said, for one dimensional body, we are having only one stress and one strain. Similarly, for two dimensional body, I am having three stresses, in which two are axial stresses and one is shear stress. Two are axial stresses and one is shear stress. Okay, so coming to the three-dimensional body, there exists a three axial stresses and three shear stresses. Corresponding to that, there is a 6 strains will be occurred. Okay, so for one dimensional body, there is only one stress, that is axial stress, that acts in the axial direction. For two dimensional body, there is 3 stresses, 2 are axial stresses and 1 shear stress. And for three dimensional body, I am having 3 axial stresses and 3 shear stresses. With corresponding to that, the strains will be developed. Okay, so as I said, as I previously we checked the cube. So sigma x plus dou sigma x by dou x into dx is the deformation produced, stress developed due to the load applied in x direction. So the total force, the total stress which is induced after load applied is sigma x plus dou sigma x by dou x into dx minus sigma x into, so as I said, force. So force is nothing but, from the Hooke's law equation I can write stress is equal to load. We know this equation, definition of stress. Stress is equal to load by area. So load is nothing but force. So from the stress equation I can determine force is equal to, see, so we know that stress is equal to force by area. So now to determine the force, I can take the product of stress into area. So if I take the product of stress into area, I can determine the force. See here, the force stress, the total induced stress in x direction is sigma x plus dou sigma x by dou x minus sigma x. The plane which is perpendicular to the stress, axial stress applied, is dy dz. So dy into dz represents the area. So since the product of force stress into area will represent the force in the axial direction. Similarly, the shear forces are developed in the xy plane and xz plane. So and body force is acting on, that is f of x into dv. So finally, substituting all the equations here, sigma x and sigma x minus sigma x will be cancelled. Tau x and minus tau xy will be cancelled, tau xz and minus tau xz will be cancelled. So then the remaining equation is d sigma x by dx into dx dy dz, d tau xy by dy into dx dz. So d tau xz by dz into dy dx into dy into dz plus f of dv is equal to 0. So since the product of dx into dy into dz will represent the total volume, so finally I can write the equation as d sigma x by dx plus d tau xy by dy plus d tau xz by dz plus f is equal to 0. So this is the equation which is developed when the force is applied in the x direction. Similarly, I can derive the equilibrium equations in all the directions. So finally, we used to get 3 equilibrium equations. Since the sum of forces in x direction is equal to 0, sum of forces in y direction equal to 0, and sum of forces in z direction is equal to 0, I can write it as dou sigma x by dou x plus dou tau xy by dou y plus dou tau xz by dou z plus f of x is equal to 0. See here, initial of differential function, I am utilizing the partial differential function. So what is the difference between differential function and partial differential function means? So if there is only one derivative, so which does not happens to change the corresponding term in the next direction, so then we can directly use the differentiation term. So partial differentiation means, so in x direction it includes the y and z planes also. So hence I am using the partial derivative which help us to only derive the x functions. So hence the equilibrium equation x direction is dou sigma x by dou x plus dou x tau xy by dou y plus dou tau xz by dou z plus half of x equal to 0. Similarly, I get y direction as dou tau xy by dou x plus dou sigma y by dou y plus dou tau yz by dou z plus half of y equal to 0. Dou tau xz by dou x plus dou tau yz by dou y plus dou sigma z by dou z plus half of z equal to 0. These three equations are said to be equilibrium equations for a three-dimensional body or three-dimensional element. And okay, so now we are going to derive the stress and strain relationship for a three-dimensional element. Okay, so we know that what is strain? Strain means nothing but generally we wish to consider strain as change in length by original length. So here the du, see here, so if you consider the small element of volume dv, the length of the element is considered as dx in x direction, so that is the true length, and du will represent the deformation produced in the particularly in the x direction. So hence the strain epsilon x can be considered as dou u by dou x, strain in y direction is dou v by dou y, strain in z direction is dou w by dou z. So shear strain can be written as dou u by dou y plus dou v by dou x, because due to the load applied displacement in x direction, what is the change obtained in the y direction? Okay, so similarly the deformation in y direction is generated due to change in the x direction. Okay, similarly I can write tau yz is equal to dou v by dou z plus dou w by dou y, tau xz is equal to dou u by dou z plus dou w by dou x. Okay, so this is the strain and displacement relationship for the axial strains and axial stresses. For axial strains and this is the relationship between the strains and displacement for axial strains and shear strains. Okay, so if arrange, we know that stress is equal, from Hooke's law we can write that stress is equal to Young's modulus into strain, Young's modulus into strain. Okay, so Young's modulus will define the relation between the stress and strain. Okay, so the Young's modulus value will represent the stiffness of the material. So if I consider a three-dimensional body, so as I said, I am having 6 stresses: sigma x plus sigma y, sigma z, tau xy, tau yz, and tau zx, and correspond to 6 stresses, 6 strains, epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. The relationship matrix which defines the axial stresses and axial strain is known as stiffness matrix, which is represented by symbol D. Okay, so now we are going to try to derive the D matrix. Okay, so we will continue in next.